Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll explain the Euler's critical load for a column with both ends fixed. Now we'll see another end conditions for the column, both ends fixed. When the column is fixed at both ends, now we have to find out the buckling load. Now once again we will consider the column with both ends fixed and taking a distance x from the bottom end, the deflection is y. Now you can see that deflected curve, initially it is straight, then it starts bending. So this end, when it comes to the fixed end, it is straight. That is because when the column tries to buckle, the fixed end will exert a resisting moment against this buckling. Okay, it can exert a reaction force in the vertical direction resisting this load applied. So this reaction will be equal to P. This is applied load, and this is a reaction. It will be equal to P, and also it exerts a resisting moment. In case of a pinned end, it will not exert this resisting moment. It can only exert a reaction force. So this moment will not come in case of a hinged end. So this is only possible with a fixed end. It can exert a resisting moment like this. This is formed against the bending. When the column tries to bend, the fixed end will exert a resisting moment like this. So even this end you will have a resisting moment Am. Now we can write the equation for deflected curve. Ei d square y by dx square is equal to the total bending moment. Total bending moment at this section. At this section, we are taking a section at a distance x. Ei d square y by dx square is plus m. So I am taking that moment of all forces with respect bottom of this section. So plus m minus p into y. So plus m minus py, that is a total bending moment acting at this section. So plus m, in the previous case it was only p into y. Now the moment is also acting, the resisting moment, reaction moment at the bottom end, fixed end is also acting, that is plus m. So m minus py, that is the bending moment acting at this section. So Ei d square y by dx square is equal to m minus py. Now taking that minus py to the left hand side, you get Ei d square y by dx square plus py is equal to m. Now dividing by Ei, d square y by dx square plus py by Ei is equal to m by Ei. M by Ei, so that you can rearrange like this. P by Ei into m by p. It is only m by Ei because p get cancelled. So I have rearranged like this. So d square y by dx square plus py by Ei is equal to p by Ei into m by p. Now this you can write it as d square y by dx square plus p by Ei, substitution is m square. So m is root of p by Ei, or p by Ei you can write it as m square y plus again here you can write m square into m by p. So d square y by dx square plus m square y is equal to m square into m by p. Now the solution for this differential equation is given by y is equal to c1 cos mx plus c2 sin mx plus m by p, this part. So plus m by p. So this is the solution for this differential equation. Now we have to substitute the end conditions to find out the constants c1 and c2. Now before substituting the end conditions, differentiating the solution which we got, dy by dx is equal to minus c1 m sin mx plus c2 m cos mx, and this is a constant part. For the applied load, m is constant, p is also constant, so differentiation of this is 0. So after differentiation you will get dy by dx is equal to minus c1 m sin mx plus c2 m cos mx. Now let us put that condition known. There is slope is 0. It is not bending at this point because of a resisting moment. The column remains straight. So slope here at the fixed end is 0. So that is true for any fixed end. Slope has to be 0. So dy by dx slope is 0 when x is 0. So in this equation you can substitute dy by dx is 0 when x is 0. So x is 0, sine 0 is 0. So this part will be 0 and this is 0. dy by dx is 0. So cos 0 is 1. So you get C2m is equal to 0. Okay. Sin mx is 0. Cos mx is when x is 0 is 1 and dy by dx is 0. So you get C2 as 0. So C2 is 0. When C2 is 0, you get the equation as y is equal to C1 cos mx plus m by p. Y is equal to C1 cos mx plus m by p. Now we also know that when x is 0, that is at this end, x is 0, there is no deflection, y is 0. So y is also 0. So at this end we have y 0, dy by dx 0. Deflection is 0. Slope of the deflected curve is also 0, that is dy by dx is also 0. So dy by dx 0, we already used that end condition. Now we are using deflection 0, x is 0, deflection is 0. So you can substitute y as 0 when x is 0. So C1 cos when x is 0, cos 0 is 1, so C1 into 1 plus m by p, or you are getting the constant C1 as minus m by p. So constant C1 is m by p and C2 is 0. Now after getting the constant, you can write down the equation. The solution now is minus m by p, that is C1 minus m by p cos mx plus m by p. Now to get a solution, we also know that at the end, at the other end, when x is L, y is 0. We have other condition, x is L, dy by dx is also 0. So that is another condition available, but you can put x is equal to L, y is 0. So that is the easiest way. X is L, y is 0. Substituting this condition in the solution, x is equal to L, y is 0. So I am substituting x is L, y is 0. So you get 0 is equal to minus m by p cos ml plus m by p, or dividing by m by p you will get minus cos ml plus 1 is 0, or cos ml is equal to 1. When cos ml will be 1, when ml is equal to 0, 2 pi, 4 pi, etc. Cos 0 is 1, cos 2 pi is 1, cos 4 pi is 1, etc. So ml when it is 0, 2 pi, 4 pi, etc., cos ml will be equal to 1. But ml is 0 is not a solution, as I already mentioned. Then load has to be 0. So the least practical value possible at which the column start buckling is when ml is equal to 2 pi. So m is root of p by ei into L is equal to 2 pi, or p by ei L square, squaring it. Okay, p by ei L square is equal to 4 pi square, or buckling load P is equal to pi square ei divided by, I have taken this 4 into the denominator, and so this is L by 2 square instead of L square by 4. I will write it as L by 2 square. So P is equal to pi square ei by L by 2 square. So I just rearranged in this form. So P is equal to pi square ei by L by 2 square. This is the buckling load for a column with both ends fixed. Euler's buckling load for a long column with both ends fixed. That's all for today. Thank you for watching.